Seki Takakazu, also known as Seki Koa, was a Japanese mathematician in the Edo period. Seki laid foundations for the subsequent development of Japanese mathematics known as Wasan, and he has been described as Japan's Newton. A contemporary of Gottfried Leibniz and Isaac Newton, Seki's work was independent. His successors later developed a school dominant in Japanese mathematics until the end of the Edo period. While it is not clear how much of the achievements of Wasan are Seki's, since many of them appear only in writings of his pupils, some of the results parallel or anticipate those discovered in Europe. For example, he is credited with the discovery of Bernoulli numbers. The resultant and determinant are attributed to him. This work was a substantial advance on, for example, the comprehensive introduction of 13th-century Chinese algebra made as late as 1671 by Kazuyuki Sawaguchi. Biography. Not much is known about Kowa's personal life. His birthplace has been indicated as either Fujioka in Gunma Prefecture, or Edo. His birth date ranges from 1635 to 1643. He was born to the Uchiyama clan, a subject of Koshu Han, and adopted into the Seki family, a subject of the shogun. While in Koshu Han, he was involved in a surveying project to produce a reliable map of his employer's land. He spent many years in studying 13th-century Chinese calendars to replace the less accurate one used in Japan at that time. Career. Chinese mathematical roots. His mathematics was based on mathematical knowledge from the 13th to 15th centuries. This consisted of algebra with numerical methods, polynomial interpolation and its applications, and indeterminate integer equations. Seki's work is more or less based on and related to these known methods. Chinese algebra discovered numerical evaluation of arbitrary degree algebraic equation with real coefficients. By using the Pythagorean theorem, they reduced geometric problems to algebra systematically. The number of unknowns in an equation was, however, quite limited. They used notations of an array of numbers to represent a formula, for example, but later, they developed a method that uses two-dimensional arrays, representing 4 variables at most, but the scope was limited. Hence, a target of Seki and his contemporary Japanese mathematicians was the development of general multivariable algebraic equations and elimination theory. In the Chinese approach to polynomial interpolation, the motivation was to predict the motion of celestial bodies from observed data. The method was also applied to find various mathematical formulas. Seki learned this technique, most likely, through his close examination of Chinese calendars. Competing with contemporaries in 1671, Sawaguchi Kazuyuki, a pupil of Hashimoto Masakazu in Osaka, published Kokan Sanpoki, in which he gave the first comprehensive account of Chinese algebra in Japan. He successfully applied it to problems suggested by his contemporaries. Before him, these problems were solved using arithmetical methods. In the end of the book, he challenged other mathematicians with 15 new problems, which require multivariable algebraic equations. In 1674, Seki published Hatsuba Sampo, giving solutions to all the 15 problems. The method he used is called Bushohu. He introduced the use of kanji to represent unknowns and variables in equations. Although it was possible to represent equations of an arbitrary degree with negative coefficients, there were no symbols corresponding to parentheses, equality, or division. For example, could also mean. Later, the system was improved by other mathematicians, and in the end it became as expressive as the ones developed in Europe. In his book of 1674, however, Seki only gave the single-variable equations after the elimination, but no account of the process at all, nor his new system of algebraic symbols. Even worse, there were a few errors in the first edition. A mathematician in Hashimoto's school criticized him, saying, "Only 3 out of 15 are correct." In 1678, Tanaka Yoshizuna, who was from Hashimoto's school and was active in Kyoto, authored Sampo Meikai, and gave new solutions to Sawagushi's 15 problems, using his version of multivariable algebra, similar to Seki's. To answer criticism, in 1685, Takeba Katahiro, one of Seki's pupils, published Hatsuba Sampo Genkai, Notes on Hatsuba Sampo, in which he in detail showed the process of elimination using algebraic symbols. The effect of the introduction of the new symbolism was not restricted to algebra. With these, mathematicians at that time became able to express mathematical results in more general and abstract way. They concentrated on the study of the elimination of variables. Elimination theory. In 1683, Seki pushed ahead with elimination theory, based on resultants, in the Kaifuku Dai no Ho. To express the resultant, he developed the notion of determinant. While in his manuscript the formula for 5 times 5 matrices is obviously wrong, being always 0, in his later publication, Taizai Sanket, written in 1683 to 1710 with Katahiro Takeba and his brothers, a correct and general formula appears. Tanaka came up with the same idea independently. An indication appeared in his book of 1678. Sum of equations after elimination are the same as resultant. In Sampo Funkai, he explicitly described the resultant and applied it to several problems. In 1690, Izaki Tomotoki, a mathematician active in Osaka but not in Hashimoto's school, published Sampo Haki, in which he gave resultant and Laplace's formula of determinant for the n times n case. The relationships between these works are not clear, but Seki developed his mathematics in serious competition with mathematicians in Osaka and Kyoto, at the cultural center of Japan. In comparison with European mathematics, Seki's first manuscript was as early as Leibniz's first commentary on the subject, which treated only up to the 3x3 case. This subject was forgotten in the West until Gabriel Kramer in 1750 was driven to it by the same motivations. Elimination theory equivalent to the Wasson form was rediscovered by Etienne Bezout in 1764. The Laplace's formula was established not earlier than 1750. With elimination theory in hand, a large part of the problems treated in Seki's time became solvable in principle, given the Chinese tradition of geometry almost reduced to algebra. In practice, the method could flounder under huge computational complexity. Yet this theory had a significant influence on the direction of development of Wasson. After the elimination is done, one has to find the real roots of a single variable equation numerically. Horner's method, though completely known in China, was not transmitted to Japan in its final form, so Seki had to work it out by himself independently. He is sometimes credited with Horner's method, which is not historically correct. He also suggested an improvement to Horner's method, to omit higher-order terms after some iterations. This happens to be the same as the Newton-Raphson method, but in a completely different perspective. Neither he nor his pupils had the idea of derivative, strictly speaking. He also studied the properties of algebraic equations, in the aim of assisting numerical work. The most notable of these are the conditions for the existence of multiple roots based on the discriminant, which is the resultant of a polynomial and its derivative. His working definition of derivative was the order term in f, accessible through the binomial theorem. He obtained some evaluations of the number of real roots of an equation. Calculation of pi. Another of Seki's contributions was the rectification of the circle, i.e., the calculation of pi. He obtained a value for pi that was correct to the 10th decimal place, using what is now called Aitken's delta squared process, rediscovered in the 20th century by Alexander Aitken. Selected works. In a statistical overview derived from writings by and about Seki Takakazu, OCLC, World Cat encompasses roughly 50-plus works in 50-plus publications in 3 languages and 100-plus library holdings. This is a dynamic list and may never be able to satisfy particular standards for completeness. You can help by expanding it with reliably sourced entries. 1683, Kenpu no Ho OCLC 0456266660. 1712, Katsuyo Sanpo OCLC 0497038813. Seki Takakazu Zenshu OCLC 0063433391. Collected works.